So now we will start the unit 8, that is atomic fluorescence spectroscopy. So first we will discuss about the origin of atomic fluorescence. The atomic fluorescence spectrum. The first one is so that is atomic fluorescence spectrum. So we know that an atom contains a set of quantized energy levels and can be occupied by electrons depending on the energy. That means different cells are there or quantized energy levels are there and the electrons are present in the different quantized energy levels. The atoms obtained by the process of atomization in a low temperature flame are primarily is in the ground state. So initially, as we have already discussed in the previous class, that the sample undergo atomic fluorescence spectroscopy or any type of atomic spectroscopy that will be first atomized. So the atoms obtained by the process of atomization in a low temperature flame are primarily that is in the ground state. So that means initially the sample will be converted, the sample will undergo atomization to convert into individual gaseous atoms, and in the individual gaseous atoms all the electrons are present in their respective ground state. Now when exposed to an intense radiation source consisting of radiation that can be absorbed by the atoms, they get excited. The source can be continuous source like xenon lamp or in a line source like hollow cathode lamp, etc., or electrode less discharge lamp or tuned laser. So these are the different source of these are the different source of irradiation that may be continuous source like xenon lamp or line source like hollow cathode lamp, or that may be electrode less lamp, or that may be tuned laser. The radiationally excited atoms, and after that, so these are the intense radiation source. From this intense radiation source, the isolated gaseous atoms will gain, will absorb energy, and they will go to excited state. Now the radiationally excited atoms, because we know that the lifetime of the atoms in the excited state is very short, and that will relax back to the ground state accompanied by a radiation. This phenomenon is called atomic fluorescence emission. So the radiative excitation or de-excitation process for for analytical AFS measurement are in UV visible range. So that means initially the individual isolated gaseous atom will undergo excitation by a particular radiation, and that will also undergo again de-excitation by de-excitation by emitting radiation. And the emitted radiation due to the de-excitation process fall in the UV visible range. The intensity of the emitted light is measured with the help of a detector which is placed in a direction perpendicular to the incident radiation and the absorption cell. Now, a plot of the measured radiation intensity as a function of the wavelength of the constituent atomic fluorescence spectrum and forms the basis of analytical fluorescence spectrometric technique. Now, first we'll discuss the types of different types of atomic fluorescence transition. So the fluorescence emission can occur through different pathways. As we have different types of atomic fluorescence transitions, the most common types of atomic fluorescence transitions are resonance fluorescence, and the next one is Stokes direct line fluorescence, then stepwise fluorescence, then two-step excitation or double resonance, then thermal fluorescence, then sensitized fluorescence. So first we will discuss about the resonance fluorescence. So the resonance fluorescence occurs when the excited states emit a special line having the same wavelength that used for excitation. That means if the wavelength of the emitted light will be equal to the wavelength of absorbed light by the atom for excitation, then that type of fluorescence is called resonance fluorescence. In the diagram, you can see the first the atom is in the ground state, that means in this energy level, that will undergo absorption of radiation by the different sources that we have discussed and undergo excitation to higher energy state. And from the higher energy state, if that will emit electromagnetic radiation in the UV visible region, then that will undergo resonance. And here you can see that the wavelength or frequency of the excited radiation is exactly equal to the wavelength or frequency of the emitted radiation. So that's why this type of atomic spectra or this type of fluorescence is called resonance fluorescence. And particularly if we consider for the sodium atom, if we consider particularly for the sodium atom, the electrons are present in the outermost electron is present in the 3s energy level, and that will undergo excitation by absorbing radiation with wavelength 285.2 nanometer, and that will undergo excitation to 3p energy level, and again that will come back from the 3p energy level to 3s energy level by emitting electromagnetic radiation of same wavelength or same frequency. So that's why that will show resonance emission spectra. So here so this is the example of the isolated magnesium atom, not for sodium atom. So that is isolated magnesium atom. So the magnesium atom showing the origin of resonance fluorescence line. When magnesium atoms are exposed to ultraviolet source, a radiation of 285.2 nanometer is observed, leading to excitation of the electron from 3s energy level to 3p energy level, and again this then emit a resonance fluorescence radiation at the exactly same wavelength, which can be used for the analysis. Now coming to the second type of fluorescence, that is called Stokes direct line fluorescence. For Stokes direct line fluorescence is observed when an atom excited to higher energy state by absorption of radiation and goes to the lower intermediate energy level by emission of radiation. From this intermediate level, it will come back to the ground state by radiation-less process. So that means here in this diagram, you can easily understand that initially the isolated gaseous atom will undergo excitation by absorbing energy from the electromagnetic by absorbing electromagnetic radiation, and that will undergo excitation from ground state to some excited state, and from the excited state, if that will come back to some intermediate state, not to ground state, if that will come back to some intermediate state by emitting electromagnetic radiation of a different frequency or different wavelength, because that will come back to the intermediate state, that will not directly come back to the ground state. If that will directly come back to the ground state, that will show resonance fluorescence, but that will not directly come back to the ground state, that will come back to some intermediate state by emitting electromagnetic radiation, and after that from that intermediate state, that will undergo radiation less deactivation. That means that will emit energy in not in the form of radiation, that may be in the form of heat energy. So by emitting heat energy from this intermediate state, that will come back to the ground state. So as when coming back from the intermediate state to the ground state, the atom will emit heat energy that cannot be analyzed through the spectra. Only the spectra can be analyzed when the atom will come back from the excited state to the intermediate state by emitting a electromagnetic radiation with longer frequency or with lesser frequency or longer wavelength, because here the energy difference between the intermediate between the excited state and intermediate energy level is less. And it can be understood by taking one example, that is the case of thallium atom. You can see for thallium atom, So the electrons are present in the outermost energy level, that is 6s to 6p2. So here, if the electron will undergo transition from 6p to 7s energy, 6p to 7s energy level by observing electromagnetic radiation with wavelength 377.6 nanometer, and that will, after that, if that will come back directly from this state to the ground state, that will show resonance fluorescence. But if that will come back from this excited state to some intermediate ground state, the intermediate ground state is 6s2p2, and here that will, by emitting electromagnetic radiation of wavelength 535 nanometer. Initially that will absorb electromagnetic radiation with wavelength 377.6 nanometer and undergo excitation, and that will come back to some intermediate lower energy state by emitting electromagnetic radiation with wavelength 535 nanometer to intermediate state. So that will show fluorescence emission. So that is called, so that type of fluorescence emission is called Stokes direct line fluorescence. And from this intermediate state, that will undergo transition to the ground state by emitting heat energy. So thallium atom is an example of atom showing direct line fluorescence, Stokes direct line fluorescence. Consider the energy level diagram for thallium atom showing in the figure 8.2b. You can observe that when excitation of radiation having a wavelength 377.6 nanometer, the thallium atom returns to the ground state in two different steps, producing fluorescence emission line at wavelength of 535 nanometer, and followed by a radiation-less deactivation which cannot be observed by spectra. Now coming to the third one is stepwise line fluorescence. So in this type of fluorescence, an atom initially excited to a high energy state by absorption of radiation undergoes deactivation by radiation less process to a lower excited state, from which it will emit radiation to return to the ground state. So initially the atom will undergo excitation by absorbing electromagnetic radiation from ground state to some excited state, and from the excited state it will come back to the intermediate state by radiation-less deactivation. These cannot be analyzed through spectra. And from the intermediate step, if the atom will come back to the ground state from intermediate step by emitting electromagnetic radiation, that type of fluorescence is called stepwise line fluorescence. So it is also a type of Stokes fluorescence. Similarly, so this type, that is also Stokes fluorescence. So the schematic energy level diagram showing the origin of stepwise like fluorescence given in the figure. So this is the figure of a sodium atom. So initially the sodium atom is an example of stepwise line fluorescence. The sodium atom, the electrons are in the ground state. The electron will be present in the 3s energy level. So the 3s electron is excited to 4p energy level by absorbing electromagnetic radiation with wavelength 330.2 nanometer. So that will undergo excitation from 3s to 4p by absorbing electromagnetic radiation with wavelength 330.2 nanometer. And from this 4p excited state, first that will come back to the electron then relaxes down to an intermediate level, that is 3. From this 4p state, that will come back to the intermediate state 3p state, intermediate 3p state by emitting heat energy. So that cannot be analyzed through spectra. Now, so here 3p is the intermediate state, and from 3p state that will come back to the ground state by emitting electromagnetic radiation with two different with two different wavelengths, that is 589.6 nanometer, and the another one is 589 nanometer. So this is the fluorescence emission at 589 nanometer, and the further relaxation from this level is non-radiative nature. Now coming to two-step excitation and a double resonance. Two-step step excitation or double resonance. In this type, so the double resonance fluorescence involves two-step excitation process using two dye lasers. That means the atom will undergo, the isolated gaseous atom or the individual atom will undergo excitation by absorbing electromagnetic radiation of two different wavelengths. So initially that will undergo first excitation by absorbing electromagnetic radiation of a particular wavelength to move to one excited state, and from that excited state if that will absorb electromagnetic radiation of another wavelength, and again that will move to still higher excited state, that is called excitation 2. So first one is excitation 1 by absorbing electromagnetic radiation of a particular wavelength, then that will undergo excitation 2 by absorbing electromagnetic radiation from that first excited state to still higher excited state, that is called excitation 2. And from the higher excited state, if the atom will come back to the intermediate state by emitting electromagnetic radiation with a different frequency or different wavelength than that of excitation 1 and excitation 2, then that type of resonance fluorescence spectra is called double resonance fluorescence. So the first laser, so here in order to the excitation process, here two dye lasers are used. The first laser excites the analyte, that means the atom, from ground state to an excited state, from where it gets further excited to another higher excited state, which helps with the help of a second laser. So the first laser will be used for the excitation of the atom from ground to one excited state, and the second laser will be used for the excitation of the atom from that excited state to still another higher excited state. And after that, from that higher excited state, the de-excitation of this higher excited state to a lower energy state is accompanied by fluorescence emission. This is called a double resonance fluorescence. Now, the excitation and de-excitation transition responsible for double resonance fluorescence are shown in figure number 8.4a. So that can be explained by this figure. Now coming to another type of fluorescence, that is called thermally assisted fluorescence. So in the thermally assisted fluorescence, the electron excited to a given level by absorption of radiation gets further excited with the help of thermal energy in a radiation less process. So that means in this process initially the atom will undergo excitation by some radiative excitation, that means by absorbing electromagnetic radiation of a particular wavelength. The atom will undergo excitation from ground state to some excited state, and from that excited state if the atom will absorb thermal energy and move to still higher excited state, second excited state, still higher excited state, and from that higher excited state if that will come back to some intermediate state, then that is called anti-Stokes fluorescence emission. And similarly, if from the intermediate excited state, if that will come back to the ground state, that is called double resonance. So here in this figure, so in this case, part of the emitted radiation has short wavelength as compared to excitation wavelength, because initially the atom undergo absorption by electromagnetic radiation and move from one ground state to one excited state, and from that excited state the atom will undergo transition to still higher excited state by absorbing thermal energy, and from the second higher excited state if that will come back to the ground state or if that will come back to the lower energy state, then that is called anti-Stokes fluorescence. The origin of this type of fluorescence in term of energy level is shown in figure 8.4b. Now coming to another type of fluorescence, that is called sensitized fluorescence. So in sensitized fluorescence, the energy of the excited atom is transferred to another atom which get excited and relaxed back accompanying fluorescence emission. So that means here S is an excited atom and A is a normal atom. If the normal atom interact with excited S atom, normal atom A interact with excited S atom, the excited S atom, if transfer its energy to the normal atom A, then the excited S atom will convert it into normal S atom and the normal A atom will convert it into excited A atom. Now, the excited A atom will come back to the ground state and will be converted to the normal A atom by emitting energy of a by emitting electromagnetic radiation of a particular frequency, and that will show sensitized fluorescence. That means the A will show fluorescence property due to presence of another excited atom S. So these are the different types of atomic fluorescence techniques or atomic fluorescence processes. Here we have detailed discussed about the resonance fluorescence, Stokes direct line fluorescence, stepwise line fluorescence, two-step excitation or double resonance, and thermal fluorescence, sensitized fluorescence. So these are very simple. So that can already discussed in the figure. So now coming to the next one is principle of atomic fluorescence spectrometry. So here we will discuss the principle. So in the principle, first we will discuss the fluorescence intensity and analyte concentration. There are two main processes involved in the fluorescence emission, which are given as absorption of radiation to generate excited atom. In order to show fluorescence emission, two different processes are there. Two main processes are there. The first one is absorption of radiation to generate excited atom, and the second one is de-excitation of the excited atom by emitting electromagnetic radiation of a particular wavelength or frequency. So these two steps are involved in the fluorescence emission spectra for any type of analyte. And we have already known that according to Beer's law, when the radiation of intensity P0 is passed through an analyte of concentration C moles per liter, then in a cell of thickness B centimeter, the intensity of the transmitted radiation by the analyte is given by Lambert's-Beer's law. Now suppose here we are considering that suppose P0 is the intensity P0 of the is the radiation intensity passed through sample under investigation, that is passed through a particular sample or analyte with concentration C moles per liter and the cell thickness is B centimeter. Then initially that will be E, so radiated by electromagnetic radiation with intensity P0. The sample is present in the cell with thickness B centimeter. The concentration of the analyte is C moles per liter. Then the intensity of the transmitted intensity of the initial radiation is P0, but the intensity of the transmitted radiation, that is P. So the value of P can be, so the value of P, that means the intensity of transmitted radiation P by an analyte, can be given by Lambert's-Beer's law. So that we have already studied. According to Lambert's-Beer's law, P equals to P naught into e to the power epsilon minus epsilon Cp. So this is the equation of Lambert's-Beer's law. Now, so P naught is the intensity of the initial radiation and P is the intensity of the transmitted radiation. So the intensity of the absorbed light, that is the amount of the absorbed light, PABS equals to P0 minus P, which is equals to, and if we put this equation here, if we put the value of P here, we can write PABS equals to P0 minus P0 into e to the power minus epsilon Cb. and which is equals to P naught whole into 1 minus e to the power minus epsilon Cp. Now, so this is the intensity of the light observed. Now the intensity of the fluorescence PF is proportional to quantity of radiation energy observed, that we have already discussed. The intensity of the radiation is proportional to quantity of the light observed. So the intensity of the fluorescence is proportional to quantity of the radiation energy observed. Now PF is directly proportional to PABS, which is equals to PABS into some constant phi. Now PF equals to PABS into phi. In place of PABS, we can write P naught whole into or P0 whole into 1 minus e to the power minus epsilon Cp. So the intensity of the fluorescence emission PF equals to P naught whole into 1 minus e to the power minus epsilon Cp whole into phi, where PF is the intensity of the fluorescence, that is the total fluorescence. PABS is the intensity of the radiation absorbed. Phi is the fraction of the excited atom that undergo fluorescence when epsilon Cb is very small. So we can write PF equals to P naught into 2.303 epsilon Cb into phi. Thus the fluorescence intensity is directly proportional to its concentration. Because epsilon is constant, B thickness of the cell B will be constant, P naught will be constant, and phi is one constant. So the fluorescence intensity is directly proportional to the concentration of the analyte present in the sample. In quantitative AFS, the instrument is generally standardized by calibration curve. The graph is drawn between the logarithm of the intensity of the atomic fluorescence signal versus logarithm of the analyte concentration. That is logarithm of the analyte concentration in the x-axis, in the y-axis, logarithm of the relative intensity of the fluorescence. And a linear relationship will be obtained for the different concentration of analyte. For different concentration of analyte sample, you will observe a linear relationship. However, it is valid only with low concentration of the element. Up to a certain low concentration, the linearity of the curve will be valid. But at higher concentration, when the fluorescence emission is high, part of the emitted light will be absorbed by the atom in the ground state. This is called self-absorption. It will lower the intensity of the emitted radiation and proportionality is lost. So that the maintain you cannot, when the concentration will be high, the linearity will be lost. But for low concentration, you can observe the linearity relationship between log concentration versus log, so relative fluorescence intensity. But when the concentration will be high, the linearity will be lost. It is due to part of the emitted light will be absorbed by the atom in the ground state by the process that is called self-absorption. So due to self-absorption, it will lower the intensity of the emitted radiation and proportionality will be lost. Further, the efficiency of the fluorescence emission phi will be lower in the atom in the excited state. Lower in the excited state lose their energy by radiation-less path or by collision with other atoms, where the energy of the excited state is transferred to the vibrational energy levels of this atom. Now, a mechanism of deactivation of an excited state is called quenching. The proportion of deactivation by quenching mechanism can be decreased by surrounding atomization flame by noble gases like argon or by using non-flame methods to convert the sample into atoms. The atomic fluorescence spectroscopy method offers advantages over the atomic absorption method as fluorescence radiation in principle as it measured against a zero background. So the atomic fluorescence in the atomic fluorescence spectrometric method, you can observe a zero background, and that's why it has the advantages over the atomic absorption method. Now coming to instrumentation for atomic fluorescence spectroscopy. So the atomic fluorescence spectrometer consists the following essential component. The first one is radiation source, second one is atom reservoir, third one is monochromator, fourth one is detection system, and the final one is readout device. The equipment is used in similar to used in the atomic absorption experiment, and expected that the detector is put in a position perpendicular to the incident radiation. A block diagram showing the different components and their relative arrangement is shown in this figure 8.6a. So in the 8.6a, the different parts of the atomic fluorescence spectroscopy is given, and similarly for 8.6b, the schematic representation of a spectrum. So this is the block diagram of the different parts of the atomic fluorescence spectrophotometer. And in the figure 8.6b, you can observe a schematic representation of atomic fluorescence spectrometer. So here this is the power supply, source power supply. This is the source, and through the lens that will go into the output device and observe the signal. Now coming to radiation source, different types of radiation source are there. When continuous source of their cathode, tungsten halide or deuterium lamp is used as a primary source, it has advantages over multi-element determination. Determination can be takes place. Here another type of that is called hollow cathode lamp, so that can be used as a source. And electrode less discharge lamp EDL, that is another type of source. Now coming to the second part, the second part is atom reservoir. In the A phase, the analyte sample is to be converted into atom vapor in the ground state before being excited by suitable radiation. That means in the atom reservoir, the analyte sample first, that the analyte will be converted into gaseous, isolated gaseous atom or atom vapors, and after that atom vapors in the ground state, and after that the atoms in the vapor state, which are where the electrons are present in the different ground state, they will undergo excitation by absorption of suitable radiation. The container or cell having these vaporized atom, that is called atom reservoir or atom cell. Let us learn about the different types of atom reservoir employed in AFS. In flame atomic fluorescence spectroscopy, the flame acts as the atom reservoir itself. So itself the flame will act as the atom reservoir. The majority of the atom fluorescence work is generally drawn in the hydrogen diffusion flame as background level. The hottest part of this flame are generally around 1000 degrees Celsius, while the bulk part of the flame is generally around 350 to 400 degrees Celsius. This permits excitation detection limits to be obtained because of the very low background. However, the analysis of these flames seriously affects the matrix effect, suffers from the matrix effect. Such flames are only really useful when the relatively pure solution is used. This can be achieved with the help of separation, isolation, or pre-concentration operation of the sample. So that means if pure solutions are used, we can use hydrogen diffusion flame. Now coming to a combination of acetylene and nitrous oxide, we have already discussed that which are the fuel and oxidizer. So this is the acetylene is the fuel and nitrous oxide is the oxidizer. And hydrogen, oxygen, argon using a rectangular flame with a premix laminar flow burner is also used extensively. The high temperature of the premix hydrogen and hydrocarbon flames gives much better atomization of many samples, but still with considerably higher background. In some of the instruments, the atom reservoirs made up of graphite are used. These are called as non-flame cells. And another type of cell that is called cold vapor cell. So these are used for the determination of mercury and involved in the conversion of dissolved mercury into elemental mercury by reacting with tin chloride, stannous chloride. And similarly, another type, hydride generation technique is commonly used for the determination of element from the hydride, for example, antimony, arsenic, selenium, and tellurium. So we can use concentration of the antimony, arsenic, selenium, and tellurium from the corresponding hydride by hydride generation technique. The next part is the monochromator. The fluorescence emission from excited atomic species is generally dispersed by a monochromator. The monochromator are the device that select a given emission of the line and isolate it from the other line. So the monochromator is the device that will select electromagnetic radiation at a particular wavelength or particular frequency, and that will isolate that electromagnetic radiation of that particular frequency from the other remaining electromagnetic radiation. Most commercial instruments use diffraction grating for this purpose. So diffraction grating is used for the purpose of generating monochromatic light. These grating instruments can maintain a high resolution over a range of wavelength. Now the next part, that is called detector. The emission radiation dispersed by monochromator or filter is sent to a detector. Here the signal is detected by photomultiplier tube, as in the same case that the flame photometry or atomic emission spectroscopy. Now coming to the next part, that is called the readout device. The output form of the detector is suitably amplified and displayed in a readout device like a meter or digital display. The sensitivity of the amplifier can be changed so as to able to analyze the sample of various concentrations. Now coming to application of atomic fluorescence spectroscopy. The atomic fluorescence spectroscopy has been used in the analysis of more than about 60 different elements present in different variety of samples. The general use of AFS to determine the concentration of the element in the sample, that is elemental analysis in favor of condition. In favorable conditions, some elements like cadmium, lead, thallium, detection limit in the range of 10 to the power minus 18 gram has been obtained. For quantitative analysis using AFF can be carried out by employing standard calibration method that we have discussed in the graph. Initially, you have to take known concentration of a particular known concentration of different solution, and they will be tested through AFS method, and and after that we have to draw a calibration curve which will be a straight line, and after that the solution with unknown concentration can be analyzed through the AFM, and that will give rise to the intensity. From that intensity we can observe what is the particular uh, wavelength of the particular wavelength of the emitted light. In a quantitative determination using high intensity cathode lamp of the element to be determined as the radiation source, a series of solution of the metal ion with varying concentration are prepared and aspirated into the flame, and the corresponding fluorescence intensity is measured. A plot, a plot of fluorescence intensity versus concentration of the metal ion is plotted. This curve give this curve is a linear at low concentration of the metal ion, but is a convex at higher concentration. So the fluorescence intensity of the solution. So if you use very less concentration, that will give rise to a linear curve. The fluorescence intensity of the solution containing the analyte is unknown concentration is measured, and the concentration of the metal ion is determined from the standard curve. Some of the application of atomic fluorescence spectroscopy in diverse areas are given, indicating the importance of these analytical methods. Part one is in the field of clinical. In the clinical use, AFS, atomic fluorescence spectroscopy, can be used for the analysis of lead, mercury, arsenic, antimony, bismuth, germanium, selenium in blood, urine, tissue, nail, hair, etc., and copper, zinc, lead in the blood serum and urine samples. Now, for environmental purpose, the AFS can be used for the determination of mercury at 1 nanogram level scale. Similarly, for the determination of arsenic, selenium, antimony, and tellurium, with the detection limit from 10 to 50 nanogram per liter, and that can detect mercury up to level 1 nanogram per liter, that can detect the presence of arsenic, selenium, antimony, tellurium with detection limit 10 to 50 nanogram per liter. Mercury in air can be determined at determined at levels as low as 10 picogram. Determination of femtogram, that is 10 to the power minus 15 gram quantities of the element in the sample by graphitic furnace laser excited AFS is done. In order to determine the concentration, when the concentration will be around 10 to the power minus 15 gram, then graphite furnace laser excited AFS techniques will be done. Now coming in the agricultural field, AFS can be used for the analysis of dairy, wine, feed, meat, cigarettes and other products for detection of arsenic, mercury, lead, antimony and selenium. Now coming to the geological and metallurgical field, the AFS is used for the analysis of ore, rock, minerals, metals for germanium, mercury, selenium, arsenic in antimony, selenium, tellurium in copper, etc. Now for pharmaceutical, AFS is used for the determination of mercury, lead, arsenic and selenium in active ingredients and fillers. Now for petrochemical field, the AFS is used for qualitative determination of mercury, lead, cadmium, arsenic, tin and zinc in fuels, lubricant and crude oils. Now for in the field of alloys, some of the example of the elemental determination of alloys like copper, iron, manganese, magnesium, nickel, zinc, etc. When combination of chromatography, AFS can provide qualitative and quantitative information of the chemical from chemical form of element, that is metal speciation in a sample. So this is the table describes the atomic fluorescence analysis in some common elements. Now coming to interference. The interferences are produced by sample matrix, that is the non-annulate component of the sample. So if non-annulate component will be present, so that will undergo interference. Interference could be chemical arising out of the molecular species containing annulate, which in turn reduce the percentage of the gaseous annulate atoms or the so the presence of interference elements. So the percentage of the gaseous annulate atom will be decreased and scattering is another area of concern and appropriate measures need to be minimize the presence of interference element. For example, a special type of spectral interference you can observe for a sample of arsenic, cadmium, cobalt, indium, cobalt, mercury, iron, manganese, nickel, tin, etc. So they will show fluorescence at similar wavelength. So spectral interference will be there. Now for chemical interference, the chemical reactions between the annulate and other component of the sample that may be reduce the number of free atoms produced and give rise to chemical interference. For example, the oxide formation can be affected the result of determination. This is because the oxide exhibit broad band absorption and can scatter the radiation, thus interfering with signal detection. Then we will discuss the merit and limitations of AFS, atomic fluorescence spectroscopy methods. The merits are the main advantages of fluorescence detection compared to absorption. Absorption measurement is generally sensitivity achievable because the fluorescent signal has much lower background as compared to that of the absorption spectra. Further, the interferences are also less in case of fluorescent spectra. AFS offer direct advantages for some metals and metalloids like lead, cadmium, thallium, mercury, arsenic, antimony, selenium, tellurium, etc. The detection limits are simple to those of the AS and AES but vary for the different elements. Better sensitivity and much lower detection limits are obtained by favorable elements like mercury, arsenic, antimony, selenium, etc. Linear curve often extended over a wide range. This may be valid over as high as 4 to 7 orders of magnitude. The sample in the solid, liquid, and gaseous state can be analyzed. So these are the different advantages or merits. When combined with separate techniques such as chromatography, the method can provide information about the chemical form of the analyte. That is the speciation studies that can be carried out in the environmental sample. Now coming to the limitations, so these are the various merits. So these are the demerits or limitations. AFS require combination with chromatography to provide information regarding chemicals from the analyte during chemical separation. Sample separation, especially for the solid, it is very tedious and time-consuming process. The analysis involved in the chemical interference due to chemical reaction between the analyte and other component of the sample, that is called the matrix, that may reduce the number of free atoms produced. Analysis of many samples, it may be necessary to correct the spectral interferences, especially when continuous sources are used. The technique is limited primarily to the determination of metals and metalloids. So this is about the atomic emission spectroscopy. So then we will discuss the next unit, that is atomic absorption spectroscopy. So here we will take just 2-3 minutes of gap. After that we will again start. Okay, so now we will start the next unit, that is the atomic absorption spectrometry. So directly come to the principle of atomic absorption spectrometry. So in atomic spectrometry, we know that in atomic spectrometry, the analyte must be present in atomic vapor state. In atomic absorption spectrometry, the atomization is performed by aspirating the sample solution to a flame where the analyte is converted into gaseous phase atom. So in the atomic spectroscopy, we have already studied that the analyte must be present in vapor state. Now in atomic absorption spectrometry, the first initially the atomization will be done for the analyte by aspirating the analyte into a flame. So initially the analyte will be present in liquid state, and after that we will aspirate the analyte into a flame that will undergo atomization, that we have already studied. Now where the analyte sample is converted into gaseous phase atom. Alternatively, the sample is fed into graphitic furnace where the atomization is achieved by electrothermally at a relatively lower temperature, that is below 3000 Kelvin. As the temperature of the atomization is low, most of the atoms remain in the ground state, which can absorb characteristic radiation from the radiation source and made from the analyte element. The atomic vapor containing free atoms of an element in the ground state. So, if we'll do the atomization in the graphitic furnace where the atomization temperature is low, so the analyte will undergo atomization and that will convert it into gas phase atoms. But all the as the temperature is low, the gas phase atoms will present in ground state. So the atomic vapors containing gas phase atoms or free atoms of an element in the ground state are illuminated by radiation source emitting the characteristic radiation of the analyte. The radiation is absorbed by the analyte vapors and the intensity decreases. This is similar to the spectrophotometry that we have learned in the previous classes. The molecules being replaced by atom here and the lab change into line source. The degree of absorption is quantized, is a qualitative, the degree of absorption is a qualitative measurement of the concentration of ground state atoms in the vapor. Now coming to concentration dependence of absorption. So the degree of absorption dependent upon the concentration of the atoms present in the analyte at ground state. The concentration of atoms with ground state present in the analyte. Concentration of atoms with ground state present in the analyte. Now, according to Boltzmann distribution law, the population of the ground state, that is the number of species in the ground state, is highest and it keeps decreasing as we move to the higher energy levels. That we have studied from the Boltzmann distribution law. It can be shown that for most of the atoms at moderate temperature prevailing in the flame, nearly all atoms in the ground state, leaving only few atoms in the excited state. The observation follows Lambert's law. So the concentration of the analyte element in the vapor phase in the flame may be determined. Now, according to Lambert's law, the extent of radiation observed by the observing species, that means how much radiation will be observed by how many observing species, that is a function of path length of the concentration of the observing medium. And mathematically, the Lambert's law can be explained as log P0 by P equals to epsilon Bc, where P0 equals to the intensity of the incident light, that is the radiant power of the incident light, P the intensity of the transmitted light, B the thickness of the observing medium, epsilon is the absorption coefficient, and C the concentration of the observing analyte atoms. Here, log P naught by P is called observance and that can be represented by A. So A equals to epsilon Bc according to this equation. Thus, the observance in the sample is directly proportional to the concentration of the analyte because A equals to epsilon B. Here, epsilon is constant and B is the thickness of the cell that is constant. Only C is the concentration which will vary. So, the observance of the sample is directly proportional to concentration of the analyte. Therefore, a calibration plot of concentration of analyte element versus the observance is drawn from the standard solution and the concentration of the element in unknown solution is read directly from the graph. However, the linear relationship between the absorption and the concentration can be observed only for all radiation passing through the sample is observed in to a same extent by analyte atom. However, experimental concentration versus intensity calibration curve is observed to be deviating from the intensity, deviating from the linearity as a result of presence of non-observed radiation or some other interferences. So due to presence of some other interferences or non-observed radiation, the intensity of the radiation will not maintain a linearity. And next we will discuss the quantitative methodology for atomic absorption spectroscopy. So like other methods of analytical methods, atomic absorption spectroscopy is not also not an absolute method for the analysis, right? So here, in order to determine the concentration of the analyte, that is, in order to quantify quantitatively, a calibration method is done, right? So the calibration can be done by three standard calibration method or by one standard calibration. So in this method, a calibration plot is drawn by aspirating the standard solution of known concentration into the flame and measuring the absorbance of each solution. So initially, the aspiration will be done for standard solution. Standard solution means with known concentration into the flame, and the corresponding absorbance will be measured. The concentrations are on. So after that, we will plot a graph where x-axis will be the concentration of the solution in microgram per ml cc or per ml microgram per ml, and the y-axis will be measured concentration in microgram per ml. So this is the actual concentration and it is the measured concentration, because for standard solution we know the actual concentration and the y-axis will be the measured concentration by AS method. By using that, we can use three standard calibration method. In the three standard calibration method, you will use three different types of standard solution. That is, for here it is given 4 microgram per ml, 12 microgram per ml, or 30 microgram per ml. And for one standard calibration, you have to use a particular solution of particular concentration. So the concentration of the unknown solution is then determined from the calibration plot. Despite the fact that Beer's law is followed in S, in practice, the departure from the linearity will be observed. The non-linearity is due to transmitted or unobserved light from the radiation source. In addition, the number of uncontrolled variables in the atomization and observance measurement may also affect the measurement. Therefore, we need to find the concentration range in which the Lambert's-Beer's law holds. We get a straight line. In practice, a single calibration does not serve the purpose. We need to take 3-4 standard different concentration and a bag to obtain suitable calibration plot. So here in the figure, a single standard calibration plot does not hold good, so that will not maintain the linearity. But if we use three standard calibration curve, we can see a linear relationship between the observed concentration, between the measured concentration and actual concentration. Now coming to internal standard method. So in this method, a fixed amount of the internal standard, which is chemically similar to the analyte being, so a fixed amount of the internal standard, which is chemically similar to the analyte being determined and observed with similar wavelength, is added to the standard solution and to the test sample. The intensity ratio of the analyte and internal solution is plotted as a function of analyte concentration in the standard solution. For example, so here, in order to understand this, we should take one example. For determination of sodium and potassium in blood serum, lithium is used as the internal standard. A typical plot is obtained in atomic observation spectrometric method. You can see here, this is the observance of the analyte by observance of the standard solution. That can be plotted in y-axis, in the x-axis concentration of the analyte. Now coming to standard addition method. In this method is specially applicable when the signal is altered by the sample matrix. In this method is known this in this method, a known amount of the standard solution of known increasing concentration of the analyte is added to a number of alicars of the sample solution. That means initially we have to take a known amount of standard solution, and after that we have to add the analyte into the standard solution by increasing so that the concentration of the standard solution will be increased, and we know what amount of analyte, we must know what amount of analyte will be added to a number of alicars of the sample solution. The resulting solutions are diluted in the same final volume and their observance are measured. After that, a graph is drawn between the observance and the added concentration of the analyte. It is then extrapolated to the concentration axis in order to obtain the shared concentration of the sample solution. So here, this is the concentration of the analyte and calibration plot of the standard addition method. So this is the observance of known concentration of the analyte the corresponding observance of the known concentration of the analyte, and that can be extrapolated to a particular concentration, so we can find out the concentration of the unknown sample. AS is a promising analytical method that is extensively employed for quantitative determination of different elements in wide range of sample. A major disadvantages of the AS measurement is that only a single element can be determined at a time as separate radiation source is required for each element. So the disadvantages is that only at a particular time the concentration of a single element can be done, and if we want to measure the concentration of different element, then separate radiation source should be used. However, nowadays the modern instruments are equipped to undertake multi-element determination. So let us know about the instrumental aspects of the AAS, that is the atomic absorption spectrometry. So here, first one we will discuss the instrumentation for the AS. A typical AS consists of the following components. The first one is radiation source, then atom reservoir, then monochromator, then detector, then the readout device. All the different parts are arranged in this schematic diagram. So, in a typical flame atomic absorption spectrometry method, the radiation from a hollow cathode lamp is made to fall on the sample to the analyte aspirated in the flame. So, initially the analyte will be aspirated in the flame and that will converted into isolated vapor gaseous vapor atoms, and after that the radiation from a hollow cathode lamp is made to fall on the sample, which is aspirated into the flame, where a part of it is absorbed. So the transmitted radiation is then dispersed in a monochromator and sent to the detector. The detector input is suitably processed and is displayed by appropriate readout device. This signal this signal channel instrument can perform measurement at a single wavelength only in one channel. Nowadays, dual channel instruments are also available that permit the simultaneous measurement of the two different wavelengths. This contains two independent monochromator for this purpose. Now coming to the radiation source, commercially available AAS use radiation source that emit characteristic spectrum of the element to be determined. So that is used in commercial AAS. So the commercial AAS, where the atomic in the commercial AAS, we should use a radiation source that emit characteristic spectrum of an element. So that means for different element we have to use a different radiation source. The essential requirement of the radiation source is that it gives a constant and intense output. There are two types of radiation sources are there. First one is line sources and continuum sources. Initially, continuum sources are used and primary radiation continuum sources were used, and the primary radiation required was isolated with a high resolution monochromator. However, these are low density and do not provide sufficiently high sensitivity. Nowadays, hollow cathode lamp, that is HCl, belonging to the first type, has been most widely used. The electrode discharge lamp, EDL, another line source that are frequently employed for the purpose and in fact superior for the element such as so this technique will be superior for the element arsenic, selenium, tellurium, etc. at low melting point. Now coming to when the bandwidth of the primary radiation is low with respect to the profile of the analyte absorption, a given amount of the analyte would absorb more radiation. Therefore, the radiation source having low width, the radiation source having low width of eliminated analyte lines are preferred. Accordingly, the radiation sources are designed so as to operate much lower temperature and pressure as compared to that of the flame and furnace used for atomization process. As a consequence, the emitted lines are much sharper than the absorption lines to be measured. In such shade, sufficient accurate measurement of the peak absorption can be made without using the elaborate optics. It is so referred as source radiation. From the figure, you can observe that a schematic diagram showing the source of resolution achieved by radiation source emitting sharper line. So here, so these are the source of so we will get sharper line, and this is the observation spectrum of the analyte. So this is the emission intensity of the initial of the electromagnetic radiation irradiated on the sample, and the sample will absorb the light at a particular wavelength, and where the absorbance will be decreased. So if the sample will not absorb, if, if the sample will not absorb the electromagnetic radiation, if the sample will not absorb the electromagnetic radiation, the absorbance will be high. But if the sample will absorb the electromagnetic radiation at a particular wavelength, there is a sharp decrease in observance of the light. And from this position, we can know that the sample can absorb electromagnetic radiation at which wavelength, and that is the characteristics of the sample. So the different parts of the atomic observation spectrometer, that is the first one is atomizer. The purpose of atomizer is to provide so representative portion of the analyte in the optical part and convert into free neutral isolated gaseous atoms in ground state. In atomic observation spectrometry, the flame and furnaces that generate a temperature in the range of 1500 to 3000 degrees Celsius are the most common method for atomization. So at this temperature, that is the most common method for atomization. Two common types of atomizers are used for generating atomic spectroscopy in the vapor phase are flame atomizer and electrothermal atomizer. Let us learn about the flame atomizer and electrothermal atomizer. First, we will discuss about the flame atomizer. So, in a typical flame atomization process, the analyte solutions are generally nebulized with the help of a nebulizer that we have already discussed in Unit 7. So, the analyte solution will be nebulized with the help of a nebulizer into a spray chamber. The aerosols so produced in the spray chamber along with a mixture of burning gases and oxidant are directed to a suitable burner as already described in the flame as already described that flame temperature depends upon depends on the fuel oxidant ratio. Requisite temperature of the analysis can be obtained by varying fuel oxidant ratio. So the fuel oxidant combinations commonly used in AS and the corresponding combustion reaction and the flame temperatures are given here. So here, so this is the combination of fuel oxidation. Here it is given ethylene, ethane, air. So ethane is the propane, air. Propane is the fuel and air is the oxidant. And here for hydrogen, air, hydrogen is the fuel, air is the oxidant. This is ethine, air, ethine or acetylene is the fuel, air is the oxidant, then hydrogen, oxygen. Then here you can see the corresponding reaction takes place between the fuel and oxidant. So here propane will undergo oxidation in presence of nitrogen gas to form carbon dioxide, water, and in the presence of nitrogen gas, and the corresponding flame temperature will be 2267 Kelvin. And you can see here the highest flame temperature will obtain in case of acetylene fuel with oxygen oxidant, and the reaction is C2H2 plus 2O2, that will give rise to 2CO2 plus H2, and here you will get 3342 degrees Celsius, 3342 Kelvin. Now coming to the burner, two types of nebulizer burners used in AS, that is premix nebulizer burner and total consumption burner. So this part we have already discussed in the previous class. Now coming to the monochromator. So the monochromator are the device that can selectively provide radiation of a desired wavelength out of the range of wavelength emitted by the source. So we know that from the source, the source will contain electromagnetic radiation with a range of wavelength. From that range of wavelength, monochromator will pick up. Monochromator will allow to pass the electromagnetic radiation with a particular frequency. In AS, the monochromator select a given emission line and isolate it from other line due to molecular band emissions and all the non-absorbed lines. Some of these lines originate from the filler gas in the hollow cathode lamp, while some other are spectral emission of the various sample component during atomization. Now coming to the next part of the instrument, that is called detector. So as the wavelength of the resonance line, as the wavelength of the resonance line falls in the UV region, the most commonly, so that means for atomic absorption or emission, whatever may be, but the resonance line will fall in the UV region, and that's why we have to use PMT photomultiplier tube detector, whose output is fed to a readout system. Then coming to the readout system include meter, chart, recorders, and digital display meter. These days, however, microprocessor control systems are commercially available where everything can be done by touch of a button. Now coming to the next spectral technique, that is graphitic furnace atomic absorption spectrometry. So here graphitic furnace atomic absorption spectrometry, in this the analyte will be undergo atomization in presence of graphitic furnace. AS used graphitic furnace, that is called graphitic furnace atomic absorption spectroscopy, GFAAS, which is highly sensitive, around 10 to 1000 times as compared to that of flame AAS, and required a very small sample. Here, a very small sample can be analyzed through GFAAS. It has further advantages are not require for it has further advantages of not requiring any sample preparation. So sample preparation is not required here. So much so that solid samples do not require sample dissolution here also. So let us discuss about the GFAAS. In the basic principle of flameless AS, similar to flame AS, the analyte is converted into, so in all type of AS, the analyte is converted into vaporized atom in ground state and are subjected to characteristics resonance by radiation emitted by a line source. So initially the analyte will be converted into vaporized atom, and as the temperature in this stage will be low, the electrons present in the vaporized atom will present in the ground state. So the absorption of the radiation and it extends from the basic analytical application. As regard to the instrumental aspects, two techniques are similar to good extent. The different being the difference being in the atomization and the atom reservoir. Rest of the component of the instrument are the same. And first we'll discuss about the different types of atomizers. First one is electrothermal atomizer, then graphitic furnace atomizer. So here it is the schematic diagram of electrically heated graphitic furnace atomizer. So here in this atomizer, the analyte sample which is initially in the liquid form will be aspirated into vapor atomic form. Next, the handling background absorption in GFAAS. So the following are the reasons for adding matrix multiplier. So in order to analyze the atomic absorption spectrometry through GFAAS, the sample will be mixed with matrix modifier, because it will stabilize the analyte during the async stage. It converts intermixing into a volatile compound that may be removed during that async stage. It helps obtain the isothermal condition in the graphite tube by delaying the analyte atomization. So here we will take just 1-2 minutes gap. After that again we will continue. So now we'll discuss the advantages and disadvantages of GFAS. So first we'll discuss the advantages. It eliminates the possibility of interaction of the sample with different component of the flame, thereby eliminating the anomalous anomalous result. No longer resident time for the analyte in the path of the incident radiation leads to a greater sensitivity. At higher proportion of the analyte sample is converted into vapor, the sensitivity is further enhanced. It will provide ability to deal with very small sample sizes. This will become quite important in the context of clinical sample because the amount of the clinical sample will be very less. And now some disadvantages. The background of the absorption effect are more serious. Analyte may be lost during ashing, especially for the volatile component. The sample may not be completely atomized. It produces memory effect within the furnace. Precision is poorer than the flame is. However, the furnace auto sampler have enhanced the precision of the furnace is. Problem due to interferences and high background may be some serious problems. Now coming to the next one is atomic absorption spectrometer. So two types of so here we'll discuss the instrumental part of the AS. Two types of atomic absorption spectrometers are there. First one is single beam atomic absorption spectrometer. The next one is double beam atomic absorption spectrophotometer. First, we will discuss the single beam atomic absorption spectrophotometer. So it consists a hollow cathode lamp, that is HCl hollow cathode lamp, a radiation source. Here this one is the hollow cathode lamp, that is the radiation source. A flame as an atomizer. So here that is a flame which is used as a atomizer, as an atomizer. That the function of the atomizer, so that will form, so that is the atomization device. And after that the analyte will be converted into gaseous, isolated gaseous atoms, then a monochromator. After that, that will pass through the grating monochromator and a photomultiplier detector and recording system. After that, that will pass through a photomultiplier detector and that will connect it to a recording system. The HCl radiation is choked to eliminate the background of the signal arising from the radiation emitted by the sample itself. Only focuses on the atomic vapor produced by the atomizer, then direct the monochromator and directed to the monochromator where the atomic lines is in interest of isolated. Now coming to double beam atomic absorption spectrometer. In this instrument, the beam of the HCl is split. So this is the hollow cathode tube. The beam of the hollow cathode tube will be split by a mirror chopper, split into two parts by mirror chopper. So this one by mirror chopper, this is the direction of the incident radiation that will split into two different radiations with intensity PR and another one is P. One half of passing through the atomizer and the other half around it is schematically. So half will be passed through the atomizer and another half will be diverted their path. The two beams are then combined by half silver mirror passed through the monochromator. The ratio between the reference and sample signal is amplified. Sample signal is then amplified and fed into the readout device. These instruments correct the fluctuations in the intensity radiation coming to the radiation source for changes in the sensitivity of the detector. Modern atomic absorption spectrometer generally have the following features. They have a lamp turret capable of holding at least 4 hollow cathode lamps that emitting absorption lines of different elements. These have an independent current stabilized supply for each element. The sample area is capable of incorporating atomizer which can work in both the flame and furnace atomizer. Improved analytical precision is obtained when the auto sampler is used in conjugation with furnace atomizer. Then monochromator is capable of high resolution is around around 0.04 nanometer. That means the monochromator, the capacity of the monochromator should be extremely high, that can undergo resolution typically in the range of 0.04 nanometer. That is a feature more desirable if AAS is adapted for flame emission and work through good resolution is also desirable for many AAS. The photomultipliers are able to function over a wide wavelength range around 180 to 800 nanometer. The instruments are equipped with background correction facility also. Now coming to the interferences of the atomic absorption spectrophotometry. According to there are three types of interferences in AS. First one is spectral interference, then chemical interference, then physical interference. So first we'll discuss the spectral interference. So these refers to the presence of another atomic absorption lines or molecular absorption band close to the spectral line of the analyte element being monitored. So this type of interference will show that there is a another atomic absorption line will present very close to the absorption spectral line of the analyte sample. It qualifies to be an interference if it is not resolved by the monochromator. As such interference occurs if a DC instrument is used and can be eliminated by employing DC instrument. Similarly, a positive interference may occur if an element or a molecule is capable of absorbing radiation from the continuous source. This may be minimized. This may be minimized but not eliminated together by using a line source. Now, another source of spectral interference is the light scattering or absorption by solid particles on vaporized solvent droplets and molecular species in the flame. This problem is significant as wavelength is less than 300 nanometer and when the solution has salt content are aspirated. This arises because of the complete desolvation of the that is called background absorption or blank. Now coming to the chemical interference. So uh, 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 the refractory elements such as titanium, tungsten, uranium, vanadium, molybdenum, zirconium, and elements like boron, aluminum, iron may combine with oxygen and hydroxide ion in the flame, producing thermally stable oxide and hydroxide. And similarly, the absorbance due to calcium is decreased by the presence of phosphate ion. The absorbance due to tungsten, vanadium, molybdenum, zirconium element and like element of boron, aluminum, iron will be decreased due to combined with oxygen or hydroxide ion to form stable species. Now physical interferences. So these are independent of the analyte type and have nearly same effect as that of emission, absorption and fluorescence with a given type of atomizer. This may be due to variation of the gas flow rate, changes of the solution viscosity affecting its rate of aspiration into the flame, which may be finally change the atomic concentration in the flame. Now coming to the sample handling in AAS. First one is preparation of sample for AAS. So this is often done by acid digestion method, which produces a clear solution without loss of any element to be determined. It is therefore essentially that all the reagent and solvents used weight decomposition should be highest purity, as any impurity may rise the blank value. So the sample should be in the highest purity form. Common acids used for the dissolution, the analyte can be dissolved in HCl solution, nitric acid solution, aqua regia, or perchloric acid, which dissolves most of the inorganic materials. For the decomposition of silicate materials, however, hydrogen fluoride must be used. So these are the different methods. So explanation of atomic absorption spectrophotometer, different parts of atomic absorption spectrophotometer, and then comparison and detection limit of the selected element by AAS with graphite furnace AS. So this one is the graphite furnace AS is highly sensitive furnace that will give the correct concentration. So here in the table it is given the comparison and detection limit of different element in GFAS. So for arsenic, the hydride generation will be 0.01 microgram per liter for in the graphite furnace. The detection limit is 0.03. Application of AS. So first we'll discuss because we know that so this AS is widely employed technique for trace and ultra trace analysis of complexes for complex matrices of geological, biological, environmental, industrial, glass, cement, marine sediment, pharmaceuticals, engine oil, or any kind of samples. It has been employed for the determination of more than 60 elements at trace to ultra trace level. So it has the capability to determine the concentration of more than 60 elements present in the sample up to trace or ultra trace level. It is frequently used for the case where the sample size is extremely small, that is in case of metalloproteins. So the table explains the resonance line and approximate detection limit of the some selected element by AAS and GFAS. Now coming to the merits and limitations of AAS. First we'll discuss some merits. So the merits of AAS are given below. So the equipment is easy to use. It, it, it is a robust technique. The technique has a small turn around it. The order of few seconds. Moderate cost analysis per sample. Low detection limit. Some of the limitations of the AAS. Requirement of furnace for the analysis of refractory materials. Use of flammable gases. Non-automated analytical procedure. Now after that we will move to the third atomic spectroscopic method, that is called atomic emission spectrometry. So here we will discuss the atomic emission spectrometry. First, the introduction. In the current unit, we take up atomic emission spectrometry that concerns the emission radiation by the suitably excited atomic vapors of the analyte. Here, the emitted radiation and its intensity forms the basis of qualitative and quantitative application. AES is one of the oldest spectrometric method for analysis. It is a multi-element analytical technique that can be used for the analysis of materials in gaseous, liquid, powder, or solid form. Its high detection power and wide variety of excitation sources make it the most extensively used method for the analysis of the various different atomic emission spectrometric methods. We will deal one of the spectrometric method, that is the inductively coupled plasma atomic emission spectroscopy. That is inductively coupled plasma atomic emission spectrometry, that is called ICP-AES. So first we'll discuss the principle of atomic emission spectrometry. The atomic emission spectrometry In atomic emission spectrometry, a reproducible and representative amount of the sample is introduced into the atomization excitation source, where it is converted into atomic vapor and the analyte in excited state. That means initially the analyte will be converted into excited state through atomization excitation source. Then flame photometry. So In the flame photometry, we know that in the previous units, on flame photometry, that the analyte solution, when introduced into the flame, undergoes a number of processes to be atomized and get excited. As the excited state is short-lived, the excited atoms come back to the ground state by emitting electromagnetic radiation. So this is accompanied by emission of electromagnetic radiation, normally in the range of UV visible radiation. Region. This radiation is characteristics of the constituent of the sample. Due to resolution of the emitted radiation that generates an emission spectrum, whose detailed analysis can be exploited to obtain the qualitative as well as quantitative details of the analyte, which will show emission of electromagnetic radiation. The versatility of AES is due to availability of wide range of atomization and excitation source. These extend forms these extend from DC arc, SC spark, or universal arc spark, or DC plasma, microwave plasma, glow discharge lamps, laser, and inductively coupled plasma. So these are the different processes of atomization excitation source. Uh, initially the isolated gaseous atom will undergo. Initially, the atoms present in the analyte will undergo excitation. Initially, the atoms present in the analyte will undergo atomization, and after that, the electrons in the ground state will undergo excitation to excited state, and from the excited state, they will come back to the ground state by emitting electromagnetic radiation of a characteristic frequency, so that is known as atomic emission spectrometry. So these are the various source of atomization excitation. After atomization excitation, that will emit electromagnetic radiation. So the atomization excitation methods are DC arc. So the analyte will undergo atomization excitation by DC arc, SC spark, universal arc spark, DC plasmas, microwave plasmas, glow discharge lamps, lasers, and inductively coupled plasma. So these are the various types of atomization and excitation sources attached to atomic emission spectroscopy. So here we will discuss the atomic emission spectroscopy based on plasma source. We know that plasma is a high energy source in which electrically neutral conducting gaseous mixtures having a significant concentration of cations and electrons will be there. As an electrical conductor, it can be heated inductively by coupling with an oscillating magnetic field. That's why it is called inductively coupled plasma. And here the analyte sample is introduced into the center of the plasma as an aerosol with the help of a nebulizer using argon glow, and after that the atoms present in the analyte undergo atomization and excitation, and after that the electrons from the ground state will excited into higher state, and after that they will show emission spectra. So this is the graph of ICP-EA spectrum of 10 ppm of cerium. Now the plasmas and its characteristics. So these are an ideal atomization excitation source would have the following characteristics. It should be completely separate and the analyte from the original matrix and minimize the interferences. It should have appropriately energy to ensure the complete atomization, but keep the atomization to a minimum. It should provide an inert environment so as to keep the undesirable molecular species formation to minimum. It should have non or negligible background of radiation. It should provide the analysis of sample in all possible forms like solids, liquid, or gases. Of course, it should be inexpensive, need minimal maintenance, and need easy operation. It is difficult to attain ideally, however. So all these criteria it is difficult to attend ideally. However, the plasma source are quite promising for the purpose of atomization excitation job in atomic emission spectroscopy. And after that, it is sustained by absorbing energy. The different plasma source, it is sustained by absorbing energy and electric or magnetic field. Three types of power source have been employed in argon plasma spectroscopy. One of the powerful radio frequency generator that powers an induction coil, and the magnetic field generated from it is in establishment with plasma. The second one is DC electrical source capable of maintaining a current several amperes between the electrodes and immersed into the argon plasma. And the third one is micro frequency generator. So these are the three types of plasma sources are there. First one is inductively coupled plasma, then direct current plasma, then microwave induced plasma. So here the three types of plasma source are given here. So this is microwave induced plasma. This is direct current plasma. By using this type of plasma source, the atoms present in the analyte undergo atomization and excitation. Now coming to the instrumentation. For a particular inductively coupled plasma atomic emission spectroscopy, that is ICP-AES. So the main parts of the ICP-AES, first one is the plasma source, an atomization excitation device, then nebulizer, a sample introduction device, then monochromator, a dispersion device, then detector, a radiation detection device, and processing and readout device. So these are the various parts. Part one is the sample preparation. The sample can be prepared by acid digestion method, dry attack method, and after that they will undergo nebulization to disperse nebulization for the purpose of aspiration of the atomized gases of the analyte into the flame. Then here different the particular nebulizer present for ICPS. So these are the two different types of nebulizer used in ICPAS, that is fleet nebulizer and ultrasonic nebulizer, then monochromator, then the detector. So the detectors are PMT, that is photomultiplier tube, photo photodiode arrays, that is PDAs, and charge coupled devices, CCDs. Then processing and readout device, we can analyze the spectra. Then types of instrument for ICP-AES. There are two types of instrument, two type of spectrometer for ICP-AES. The first one is sequential spectrometer and another one is simultaneous spectrometer. So in the sequential spectrometer, so this instrument is used movable grating monochromator to select the wavelength of a sequential order and use the single photomultiplier tube to detect them. But in simultaneous spectrometer, these instruments are designed to simultaneously measure the response at different wavelengths so as to overcome the drawbacks of the sequential spectrometer. So again, the simultaneous spectrometers are of two types. These are polychromators, solid state array based spectrometer. So this is the schematic diagram showing the layout and optical diagram of ICP polychromator. So these are the various parts. Now coming to the analytical methods in ICP-AES. So that can use for qualitative analysis using ICP-AES. So in the qualitative analysis using ICP-AES, so this technique has not been exploited for the principle. In principle, it is possible to obtain qualitative information for ICP emission spectrometry by using sequential spectrometer. However, this technique has not been exploited for this purpose. This is so because the amount of the sample and instrument time required are prohibited. Similarly, it is most impossible to install the individual photomultiplier to monitor multiple lines of each possible element is in interest. So the qualitative analysis is based on the principle that each element has a characteristic spectral consisting most persistent lines and the characteristics lines. So they are used to identify the presence of an element in the analyte. So these techniques are used to identify the presence of one element in the analyte or not. The most prom- the most persistent or RU lines are the ones that persist even when the concentration of the respective element are progressively reduced to zero. The RU lines are not necessarily the most intense lines. And then quantitative analysis of the ICP is can done by calibration curve like these types of calibration curve obtained for tracer element analysis. So these are different types of calibration curve. Now interference of ICP. So here also spectral interferences will be there, and physical interferences and chemical interferences are there. Due to that this type of interferences, there is a decrease in intensity of the emission line. Now application of ICP in agricultural science, analysis of agricultural products and foods besides soil analysis, healthcare. It is used in detection of aluminum in blood, copper in brain, selenium in liver, sodium in breast milk, etc. Direct determination of calcium, iron, copper, magnesium, sodium, potassium in serum sample. So geological application, presence of lanthanides and other elements in rock sample. Forensic application, crime scene soil analysis. Metallurgical application, analysis of trace element in stainless steel. Environmental application, wastewater analysis, determination of pollutant metals in variety of matrices. For industry, the presence of metals like copper, iron, nickel, silicon in lubricant oil or gasoline, even in tracer component, even in tracer concentration. So these metals like tracer metals like calcium, copper, iron, manganese, magnesium, phosphorus, potassium, zinc. Determination of the trace element in polymer and trace element in polymers and evaluation of catalyst and so on. So these are the various application of AES. So then we'll move to the next unit is mass spectrometry and NMR. So mass spectrometry and NMR we will discuss on Monday. So here we'll stop and we'll discuss the mass spectrometry and NMR on Monday.